Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to find the local extrema of a function using the second derivative test, how to determine the concavity, and also how to find the points of inflection. So let's take a look at the instructions for the example. For the given function, A, find the extrema using the second derivative test. B, find where the function is concave up and concave down. And then part C, state the points of inflection. Basically the x-coordinates of the points of inflection. So for this example, the function under consideration is f of x equals x to the fourth minus 8x to the third plus 4. Alright, so first thing we want to do, we want to find the extrema using the second derivative test. What on earth is that? What is the second derivative test? Well, let's go ahead and write that down real quick so that we know where we're going. Okay, so second derivative test. Okay, so the second derivative test, the initial condition is if f prime, let me rephrase that. If x equals c is a critical point, if x equals c is a critical point, what does that mean? That means that at x equals c, the derivative is 0 or does not exist. Okay, so if x equals c is a critical point, then f prime of c is equal to 0 or it does not exist. That's what it means to be a critical point. So if we have this initial condition, then part I, if the second derivative at that critical point is less than 0, if you have a negative sign to your second derivative at that critical point, what we have is a downward facing concavity, okay? If the second derivative is 0, so you're going to be concave down. So what kind of extrema is that? That implies that x equals c is a local maximum. Okay, so if the second derivative is less than 0 at a critical point, we have downward facing concavity, which means that we have a maximum at that critical point. All right, part 2, if the second derivative is greater than 0 or positive at that critical point, then x equals c is a local mean, or you can also call it a relative mean. Relative mean, they mean the same thing, okay? Relative mean here, or call that relative max. All right, my R looks like a V. All right, so for this problem, all we have to do is find the critical points and find the sign of the second derivative at those critical points, and that will help us determine part A, our local extremas, using the second derivative test. All right? Okay, so let's go ahead and do the first part. I want to find the critical points. All right, so how do we find the critical points? Just find the derivative. So that's the function. So f prime of x is going to be, using the power rule, 4x to the third minus 24x squared. All right? So to find the critical points, we need to find where f prime of x is equal to 0, horizontal tangents, or f prime of c does not exist. We have corners or vertical tangents. All right, let's do the first one. We're just going to take the derivative for x to the third minus 24x squared, set it equal to 0, factor and solve. Okay, we can factor out 4x squared here, and then we have x minus 6 equals 0. Using the zero product property, for x squared equals 0, or x minus 6 equals 0. We solve the first equation by dividing by 4 and taking the square root. You have x equals 0. Add 6 to both sides here, x equals positive 6. So these are critical points where the derivative is 0. Now where is the derivative undefined? For this function, we know that it's smooth and continuous. There are no vertical tangents. Cross for corners is just a typical cubic function. It looks something like that. So when is it undefined? This is defined for all values of x, so never. All right, so these are our critical points. Now we have the first part of the second derivative test determined. We have the critical point. Now we need to determine the sign of the second derivative at these points. All right, so we're going to find the second derivative next. Let's write down the instructions. Find the second derivative. Okay, find the second derivative. All right, so in this situation, we can just say our C's for the critical points are 0 and 6. Okay, so let's find the second derivative, and then we can do the test. F double prime is simply going to be, we're differentiating this function up here. We have 12x to the second power minus 48x. All right. So what are we doing with this function right here? We want to find the sign of the second derivative at these two values so that we can know what kind of extremas they are, if they are actually an extrema. Okay, so first one, f double prime of 0. F double prime of 0 is, we'll just substitute 0 for x in this expression here for the second derivative. 12 times 0 squared minus 48 times 0. Okay, so what do we get? We get 0. So it's neither positive nor negative. So even though this x equals 0 is a critical point, it's a potential extrema. So is it an extrema? The answer is no, because the second derivative is neither positive nor negative. Okay, and then let's test the second point, the second critical point, f prime of 6. We have 12 times 6 squared minus 48 times 6. Let's see what's this. We actually have to work this out so that we know what the sign is. Is it positive or is it negative? So let's see what this is. Well, since we just want to find the sign, I can, let's see if we can determine what the sign of this expression is, okay? So I can write this as 12 times 6 squared, and then I can factor out a 4 from this 48, so this becomes minus 4 times 6 squared, okay? If you don't want to use a calculator, you can basically use your number sense skills to determine what the sign of this resulting answer is. Okay, so I can see, writing it in this format, we can see that this term is bigger than this term, so the second derivative is going to be positive. Okay, it's going to be positive. All right, so now we have to write down what our results mean. So let's go ahead and write that down. So since f double prime of 0 is equal to 0, and um, and x equals 0 is a critical point. What's the conclusion here? Is it a max or is it a min? If x equals 0 is a critical point and the second derivative is 0, which means it's neither negative or positive, x equals 0 is not a local extrema. Okay? It has to either be positive or negative in order for us to draw any conclusion as to if it's a max or a min. Alright? So since it's 0, it's not an extrema. Alright, secondly, since f double prime of 0 is, f double prime of 6, we're looking at 6 right now, f double prime of 6 is positive, okay, is greater than 0, and x equals 6 is a critical point, what conclusion can we draw here? X equals 6 is a, remember, if the second derivative is positive, we have an upward facing concavity, which means that that extrema is a low point. All right? So x equals 6 is a local minimum. All right, so that's that for the A part. Now we're going to shift our attention to the B part. What are we to do there? Let's go back to the question. Find where the function is concave up and concave down. All right, so when is the function concave up or concave down? For the B part, we're going to be using the concavity test, okay? Concavity test. So what is the concavity test? Let's go ahead and write down what the concavity test is. Concavity test. If the second derivative is less than 0 or negative on an interval I, then that implies that the function is concave down on I. Okay? So negative, concave down, like negative people are always sad, so concave down. All right? And then if the second derivative is greater than 0 on that interval, that implies that the function is concave up on that interval. Okay? So think about it. Positive people always happy. Negative people sad. Okay? So concave up for positive second derivative, and then concave down for negative second derivative. So what this is telling us is we just need to find the intervals where the function, the second derivative, is positive and negative to determine where it's concave up or concave down. So the second derivative is 12. Let's see, what was it? Let's go up a little bit. Oh, there you go. 12x squared minus 48x. 12x squared minus 48x. Now, let's see. We want to see the intervals where it's neither negative nor positive. Okay? So if we can find where it's neither positive nor negative, then we know the intervals where it's either positive or negative. So how do we find the points where this function is neither negative nor positive? Oh, we just set it equal to 0, right? Because when you have a value of 0, you have no sign. Set this equal to 0, factor and solve. You can factor out 12x here, and we have x minus 4 equals 0. If you solve this using the zero product property, if you solve this one right here, you have x equals 0, and then this one right here, you have x equals 4. So what is the significance of these two values? Well, these are the points where the second derivative is neither positive nor negative. The function is neither concave up nor concave down. We want to know what's happening around these points. Another way you can look at these points, you can call them our potential points of inflection. Okay, potential points of inflection. Remember, concavity must change in order for a point to be a point of inflection. All right, so these are potentials. They're not, we don't know yet until we make our sign chart. Okay, so we have 0 and 4. We have interval 1, 2, and 3 that we're going to be testing. All right, so what we are looking for here is the sine of what? Sine of the second derivative. That tells us the behavior of the function. Okay? All right, so interval 1, let's test -1. Interval 2, so here test -1. Interval 2, let's test x equals 1. And interval 3, we can test x equals 5. All right? So remember, all we care about is the sign of the second derivative. All right, so let's do this on the side right here. Second derivative again. Let me write it in its factored form so it's easy to tell what the sign is without doing much work. For interval 1, we're doing f double prime of -1. So we have 12 times -1 times -1 minus 4. Okay? So what do we have here? We just want to know what the sign is. Is this positive or negative? This is negative, and this is negative. Negative times a negative is positive. Okay? Interval 2, f double prime of 1. We have 12 times 1 times 1 minus 4. Okay? So 12 times 1, this is positive, this is negative. So our sign is going to be negative. Okay? So positive times negative, negative. Good. And then for interval 3, f double prime of 5, we have 12 times 5 times 5 minus 4. So we have a positive number times a positive number, which is positive. All right, so now we have sign of f double prime is positive, negative, positive. Now what does that tell us about the behavior of f? So we're using the concavity tests right now, okay? So if f double prime is positive here, f is concave up, negative, concave down, positive, concave up. All right, so let's write down our answer. For part D, f is concave up on negative infinity to 0, union 4 to infinity. And then f is concave down on the interval 0 to 4. All right? All right, and then the last part C, we want to find the points of inflection. Points of inflection. All right? So if the second derivative changes signs at a point, that point is a point of inflection, okay? So what you notice here is that the second derivative changes sign at 0 and 4. So those are our points of inflection, okay? So x equals 4. Now let's write in order. X equals 0 and 4 are points of inflection. Inflection since the second derivative f double prime of x changes sign. Okay, from positive to negative and then negative to positive. That's enough to conclude that they are points of inflection. So that's that. Thanks so much for taking the time to watch this presentation. We really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on mathgotserved.com. If you have any questions, comments, or requests, feel free to include it in the